Part 1. Determine the spring constant from simple harmonic motion. The objective of this experiment is to determine the spring constant of a spring by measuring the period of a mass spring system. Suspend a spring from the ring stand. Then, position a motion sensor directly under the spring. Then adjust the software controlling the motion sensor so that it collects data at a rate of 10 Hz. Hang a 100-gram mass and record the period using the motion sensor software. The period recorded for the 100-gram mass is 0.7 seconds. To calculate the spring constant using the mass spring method, we input these values into the equation K equals 4 pi squared m over t squared. Here, m is 0.1 kilograms and t is 0.7 seconds. Therefore, the spring constant is 8.057 newtons per meter. Then repeat for a 200-gram mass. The period recorded for the 200-gram mass is 0.9 seconds. To calculate the spring constant using the mass spring method, we put these values into the equation. Here, m is 0.2 kilograms and t is 0.9 seconds. Therefore, the spring constant is 9.748 newtons per meter. Then repeat for the 250-gram mass. The period recorded for the 250-gram mass is 1 second. Input these values into the equation. Here, m is 0.25 kilograms and t is 1 second. Therefore, the spring constant is 9.870 newtons per meter. Then take the average of the three spring constants. Part 2. Determine the spring constant directly. The objective of this experiment is to determine the spring constant of a spring directly using the principles of Hooke's law. This time, instead of a motion sensor, attach a ruler to the ring stand. Hang a 100-gram mass and record its displacement. The displacement for the 100-gram mass is negative 16.15 centimeters. For the equation, m is 0.1 kilograms, so F is 0.98 newtons. X is negative 1615 meters. The constant is 6.068 newtons per meter. Repeat for the 150-gram mass. The displacement for the 150-gram mass is negative 24.35 centimeters. For the equation, m is 0.15 kilograms, so F is 1.47 newtons. X is negative 0.2435 meters. The constant is 6.037 newtons per meter. Repeat for the 200-gram mass. The displacement for the 200-gram mass is negative 33 centimeters. For the equation, m is 0.2 kilograms, so F is 1.96 newtons. X is negative 0.33 meters, and the constant is 5.939 newtons per meter. The percent error is 53.3%, which is a very large percent error. In our experiment, we determined 9.225 newton meters as the spring constant using simple harmonic motion. We determined the value 6.015 using Hooke's law. We had a percent error of 53.3%. This may have occurred because of an error in the placement of the motion sensor under the spring during simple harmonic motion. Amplitude does not affect period. With a small amplitude, a mass will gently move back and forth. With a large amplitude, the mass will move back and forth with a greater speed, not a greater period. Thus, amplitude does not affect period, as it is the speed that changes along with the amplitude.